Hello, this is Daniel Howard. I'll be talking about leveraging profiling tools for OpenACC refactoring projects. This is a project extending on PRIMo, a flood inundation model, which stands for Parallel Raster Inundation Model. This was supported by my colleague Davide Davanto, also at NCAR, as well as then Brett Sanders and his former PhD student Adam Luke from UC Irvine. Brett Sanders, as well as Joe Schubert, were primary developers of the PRIMo model. And we had additional support then from Dave Norton, Matt Stack, and Mahidar Tatneni during the SDSC GPU hackathon. We very much appreciate for their additional support and encourage others to continue to participate in the hackathon events, as it was very important, useful for our own project and improvement of our PRIMo model. I'll briefly explain at least the background of PRIMo. It is a explicit finite volume scheme in order to solve shallow water equations for flood events like during Hurricane Harvey. It's done on a Cartesian grid and uses compute-intensive algorithms like Riemann solvers, as well as a more novel approach as detailed in Sanders and Schubert's paper for a dual grid implementation, which requires a linear interpolation in order for processing downscaling from the primary grid to the subgrid. This initial approach utilizes single process multi-data design with MPI domain decomposition, utilizes no libraries and was all in Fortran. Given it was a SPMD design, this made it rather straightforward in order to implement using OpenACC to run the model on a GPU. Thus, that was where our focus was on, to create a performant model on a single GPU. And in the future, we plan to still implement the model on a multi-GPU version with MPI and OpenACC. Our refactoring workflow they ended up going through, when we look at the code, it initially involves initial loading of raster data. This is outside the scope of OpenACC, but parallel I/O, for example, in this region of the code, could be a separate goal later in the future for further optimization. The primary target for OpenACC was the main time spent loop and associated runtime routines, including like the Riemann flux solver routine, which initially I had thought would be one of our main crux points for focusing on optimization. Nonetheless, when doing this sort of approach in refactoring, we have a suggested approach towards doing that effectively, so you can make the best use of your development time and resources. It's useful to initially just add the ACC kernels or parallel regions around where you want to where you have parallel code to run without using the data regions. When you first add these kernel regions, you then just verify the correctness of the code. You can use TA autocompare, which allows you to run a CPU version of the code and a GPU version of the code simultaneously, and then compare output of each to make sure that there's no discrepancy between each version. Once that is done, and you're confident that the code is still correct, you can then add the ACC data regions to minimize data movement and verify correctness again and iterate. Essentially, by just following that process, starting with just the kernels and parallel regions, this forces the compiler to be sure correctness by copying all needed variables as you enter, and then copying out the variables as you exit the parallel regions. However, this can often be redundant and will then initially slow down your model, oftentimes much even slower than the CPU version. But if you don't follow these sort of steps one by one, it might be harder to isolate bugs if something goes wrong in terms of how you've chosen to implement your OpenACC refactoring. So in our case for PRIMo, we basically had a big data class around a main time loop. And within the time loop, we had our functions that each had their GPU kernels inside such functions. If we had any CPU code, we'd surround that CPU code with appropriate data movements as we needed, and making sure to minimize those movements as much as possible. In this case, the max lambda variable there was just a single variable. It wasn't like an array, so it's not that much of an impact towards data movement. But nonetheless, that data clauses can be as big as you want. Like in our case, we actually could surround the whole time loop and the whole compute intensive region of the model, since the GPU memory was able to hold that all. However, if you do choose that approach, that is just something to consider in terms of like how big of a model you're running and whether or not the GPU can hold that. But if it can, this makes it much easier in terms of tracking data going in and out of the GPU, and without having too much of a concern throughout the majority of the model, and just letting the GPU run everything as much as possible and minimizing the amount of CPU code. But overall, this is about the profilers, and the profilers, as we used throughout this development process, was actually pretty useful for helping us identify quickly where we might needed additional work and where problems were arising. The NVIDIA Insights ecosystem is included within the NVHPC SDK, which is free for individual users as well as for HPC centers. The SDK itself includes these profilers. So an individual user, say, could run their model on a HPC cluster and then download the reports onto the individual system and analyze them from there without necessarily having to go through a VNC session or an X session to do that analysis. It is usually useful to focus first on the NSight systems, which gives a more broader overview of the performance of your model. And then as you identify particular kernels or sections of your code you want to further analyze performance on, you then run NSight compute on those individual kernels to understand further performance metrics about your model. Running the NSys profilers or NSight compute model profilers is rather simple. It typically entails just prepending your executable or MPI run executable with NSys profile. There are other options you can use and look into by looking into NSys-help, or you could consult the online documentation. But a common set of argument flags you might include is included at the bottom here, which just indicate the output file name, as well as like what type of code and functions you basically want the profiler to be looking at or tracing, or even like say tracking the amount of memory usage throughout the runtime and see how much memory is being utilized on the GPU and maybe how much you might have them left to use if you say want to down the line increase the fidelity or the amount of data you're sending to the GPU to process. So when we initially run the NSight systems profiler, this is the output we kind of got. So as you can see here, we have this advanced routine as we zoomed into the profile that's taking a majority of the time. And actually, if you look at the visual display, you don't even see the other kernels that are running. You can look down at that lower table there. You can see that the advanced routine is taking about a half a second, 500 milliseconds. But most of the other kernels and functions that are being profiled are taking on the order of microseconds. So obviously there was an issue in the advanced routine that we wanted to address. Luckily, that was easily able to be identified in the sense that OpenACC will automatically name these kernels based on the subroutine and line number. So you don't necessarily have to do additional steps to like help the GUI tell you where exactly your problems rely. But nonetheless, if you want to say further isolate within sections of your code using the NSight systems profiler, where performance and time is being spent, you can use the MVTX ranges and linking the MVTX library or compile time in order to define within your code with additional function calls, different sections of the code, say like around, say, the Riemann solver or around a particular compute intensive function, et cetera, things like that. And that can help you say further isolate maybe where a problem might be without having to go further in terms of guessing maybe where within a specific kernel an issue might be. So in this case, we knew it was the advanced routine that was a bottleneck. In terms of further analysis and analyzing that, we shall go into more detail with NSight compute later. We determined that it was causing excess data when we were calling this VFR routine within that advanced subroutine. We had been using the ACC routine declaration in order to have the GPU compiler make GPU code for that VFR function. But when calling that specific function, we actually were passing in a small slice of an array for what data would need to be processed in this case. And in so doing, that subset, at least in Fortran code, that slice of it that was being passed was causing a lot of new sub-data objects to be instantiated each call, and thus then slowing the program. So in realizing that, we actually ended up just inlining that function, and that actually resolved that problem much more effectively without necessarily any other complicated issues. But using the profilers, we could more easily identify that as being the problem than, say, a different kernel where maybe we thought it might have been the problem. Since the advanced routine actually wasn't running, say, the Riemann flux solvers, it was actually in different routines. So if we had not run this profiler initially, we might have, say, tried working on other kernels and try to improve those first rather than focusing on where the actual problem was originally. So after we inline that VFR function, we actually see a much better output from the NSight systems profiler. All the routines are actually like visible, and like as you zoom in, and they're each of comparable size, and they actually match to a original profile run using ARM Forge on the CPU only version of the model. Nonetheless, as you can see here, further optimizations could be pursued as you say look at each particular kernel and identify, say, that most runtime is spent within the advanced as well as in the flux routines. If you realize that, say, certain routines are independent of each other, you might try even running, letting the kernels be run asynchronously. with CPU and GPU code as available. But nonetheless, just with this, some of these initial fixes and additional work that we had done, we were able to achieve a 56x speedup for one V100 GPU versus our one CPU use case for the model on our Hurricane Harvey test run. However, this speedup does not include the initialization or I/O portion of the code, but nonetheless, it was still very significant and meaningful towards the work we were able to do so far in terms of optimizing the model. To further analyze the model, you can then run NSight compute. Again, you can see the docs to see additional information, but an example set of function flags when calling NSight compute is given above. You might find useful to just by default always use the --set full option, which is basically tells the NSight profiler to analyze all metrics available to it that can eat up more time in terms of how much time the profiler takes to actually go through your model. But if you have the resources, that could just be a default option that's available to you. As well, other interesting and useful flags include the kernel regex option, which allows you to specify specific kernels only to analyze. So otherwise, if you don't do that, it'll just analyze every single kernel it encounters. And that can become very tedious and time consuming if the NSight compute is allowed to just go through every single kernel it encounters. So in any case, this is the initial output you would see on the first page of the NSight compute GUI. In this case, we actually combined the inline version to the functional version. So there's an option to set like a baseline of performance within NSight compute. So then you can compare one model report to say revise or improved one. So in our case, we have the inline VFR version, which is the purple, the function VFR version, which is the purple bar graphs, and the blue ones are the corrected and inline version. So we can see we achieve a much greater memory throughput compared to peak theoretical max. However, the streaming multiprocessor utilization rate, the SM% there, is still very much still pretty low. And this actually indicated to us that the model that we were using, though it was a pretty sizable test case, was actually not large enough to utilize the full capability of the GPU. We were able to run additional tests without concern in terms of putting more higher fidelity and larger models on the GPU without further concern, and thus being able to achieve greater SM% throughput there, utilization rate. But this initial GPU speed of light graph will at least point out where there's a problem, but might not be specific enough to identify where the problem might be. That you can try to look through some of the percentages and options there below. But as you say, exploring the data here, you can always look at the GUI will give you recommendation flags, these little yellow signals that they'll point you maybe in the right direction. But you can also hover your cursor anywhere in the GUI for additional details on a specific metric that's being provided. But the next page right below the speed of light is the roofline analysis graph. So you can see here that in both cases we're still bandwidth bound versus compute bound, but nonetheless we still see great improvement from the function VFR version versus the inline VFR version. And so that is very reassuring to see, at least in terms of the measurements provided by the profilers themselves. Additional data, say like in terms of looking at the memory movement throughout the program model, can be seen in the memory workload analysis section. Further details in terms of like analyzing that is perhaps a little convoluted, but at least you can more easily say identify where say cache misses might be prevalent depending on how much data is being moved between different caches within the GPU. But one of the main things at least always to look at is like the memory throughput there at the top left. That at least in this case is like 685 gigabytes per second, but as we saw earlier, that was around still only 80% of the max throughput achievable by V100 GPUs. And you can always look up on the data spec sheets for whatever GPU you're on what the actual memory throughput is. Given that we had like a 3,000% improvement from initial implementation, that was very much useful to us and valuable. So further work in terms of like analyzing this particular section was not necessarily useful. But there's lots of information here to sift through as you might be interested in. Further sections highlight the improvement and utilization of floating point operations by the corrected version versus the non-optimized version, where more time is spent in, say, like load store operations and moving data around, or in the CBU section, or types of operations. That was actually a barrier type function that's called when data is being weighted to move around as computations are processed. So when we made that fix, we actually saw that this significant improvement towards like actually doing compute intensive work versus all the other operations that the GPU was trying to do with the non-optimized version. So these are sort of things that sort of like can point you in that direction. They're not exactly the most easily interpretable, but nonetheless, there's always hints that they're given, but it at least can give you an idea of different issues that you might be trying to address as you're making improvements in analyze performance. One of the most like interesting sections or useful to most people, I would say, is the source counter sections, which can at least give you a specific line in the source code where time is being spent most significantly. And so this can actually like point you where, say, the hotspots are in your code, given the sampling data collected by the profiler. However, you can go to more detailed outlook on like the source counters, for example. If you go to the top left of your GUI and click the details drop down and change that to source, you can then have you can go like directly to the source code itself of your model, so long as you link it appropriately within the GUI interface. You can see where these hotspots are within the code itself. So in this case, you see our function VFR version analysis. Even though it's commented out there, I was just linking to our fixed code. You can see it spent a lot of time just simply calling that function and not actually spending a lot of time in the computing anything within that function. So once we actually inlined that and corrected that, we see that call is no longer there as an issue, obviously, but it's now spending like just reasonable amount of time doing whatever computations are needed to do within that function, without spending that significant time creating those sub-slice arrays that would be passed into that particular function there. So this is just one way, you can go through line by line and see where those hotspots are and help you identify maybe where one function might be computationally inefficient, and thus you might look for a different representation of how you're doing some computation, or trying to eliminate redundancy in data computations. This sort of analysis can at least help you specifically identify those specific hotspots. And even though this is all in OpenACC, you actually then converted in CUDA code, which you don't see, the way in which the profiler is able to highlight which specific lines of code where time is being spent is still useful, despite not having that CUDA aspect. If you are a CUDA programmer, would like to see more of that nitty-gritty implementation part, this is still, I think, effective for most use cases of OpenACC developers. As you said, less profiler data. What's important? Three things I think important to focus on: occupancies, that's the SM percentage. So it's the active threads versus max number of threads per compute unit. It's important to check whether those GPU SMs are kept busy. So if they're not being kept busy, try adjusting the work group size or kernel resource usage. You could maybe throw more data to the GPU, basically, if you're low SM percentage. So basically, if you see a low percentage there, it just means you can push more compute intensive workloads onto the GPU. Essentially, maybe in our case, a larger or higher resolution model that you can perhaps run without necessarily impacting data movement too significantly. You might also look at like issue efficiency. Look for there are specific sections within the profiler that look at say issues like memory dependency or constant cache misses or texture busies or pipeline busy operations. And when you see those sort of issues maybe starting to pile up, you want to look into where that might be happening, say within like the source code analysis section, and try to fix those issues specifically. But as I said, you can like highlight over specific metrics that are being measured, and thus then use that detailed tooltip page that pops up to help inform you what exactly might be causing that problem as you see each of these individual issues. Lastly, peak bandwidth percentage. You want to make sure you're actually getting close to the theoretical max bandwidth of that GPU to make sure it's actually pumping through the amount of data as fast as possible. If it's not achieving that max throughput percentage, you want to look into coalescing memory loads, storing values in local cache memory using perhaps the OpenACC cache directive. And then, of course, which is the main thrust of when using OpenACC is making sure to reuse data and minimize host-to-device or device-to-host memory movements. So overall takeaways, when refactoring GPU codes, take incremental steps. You can, as you're taking these incremental steps, making sure you can use the TA autocompare tool in order to ensure that correctness is achieved throughout the development process. Always minimizing data movements. You can even put your data region environment on the largest section of code as possible, so long as there's enough GPU movement, memory available. So that's a approach to consider in terms of when doing a refactoring project. Then, of course, as you're going through development, making sure you're running NSys or NCU as you're analyzing, and hopefully then throughout the refactoring process, making your model actually faster. This at least helps you isolate faster which parts of the code might need additional work without necessarily having to guess where maybe your problem might be. Nonetheless, the compiler can still implement code inefficiently, so the NCU, the NSight compute profiler, can be much more effective towards identifying where maybe those inefficiencies can lie and maybe how to correct that. The last two recommendations, the GPU hackathons program is actually very effective in terms of just setting aside specific time and putting out a game plan for how to focus on improving a model and actually making progress and say refactoring, or what you might be hoping to achieve to do and making performant GPU code. But lastly, excessive time spent optimizing is not as important as just implementing good software engineering practices. You want to make sure your code is well documented, is commented, it's made accessible to other people down the line. When you actually are, say, maybe publishing a paper about your model, be useful to, over the course of the development, have that model be ready for, say, public scrutiny and availability actually to other researchers, so that they might be able to replicate and reuse your model and data as you had originally intended. And that can only be achieved if you promote good software engineering practices throughout your development process. Anyways, here's some last useful resources, which include some textbooks, some courses and online webinars and blog posts. One I recommend specifically, a YouTube series of videos from a UIUC electrical engineering course on the use of NSight profilers that goes much more in depth than I have time for about the specific metrics being measured and how that might be useful towards analyzing different steps that you could take towards further optimization. Definitely many places you could look into towards finding how to use these tools effectively. The documentation itself that's provided by NVIDIA is very useful towards understanding the tools directly, perhaps getting to more complex use cases for your specific project. Anyway, thank you for your time. I'm happy to take any questions. And this last picture here is just an ode to OpenACC during our group hike at the Rocky Mountain National Park, following my initial exposure to OpenACC at the 2017 International HPC Summer School, at which I was very appreciative for the teachers and mentors there for providing student experiences and learning programming paradigms like directive-based approaches of OpenACC. Again, thank you for your time and happy to have any questions.